FM5 1 Unbiased Estimators. The syllabus asks for us to understand and use unbiased estimators, to understand and use a variance criterion for choosing between unbiased estimators, to understand and use unbiased estimators of a probability and of a population mean and their standard errors, and then to understand and use unbiased estimators of the population variance. So for t to be an unbiased estimator of theta, then the expected value of t must equal theta. And if we are comparing two unbiased estimators, then the one with the least variance is the best estimator, closer to the true value. Reminder of expectation algebra that you might need along the way. Variance of x is equal to expected value of x squared minus expected value of x all squared. The expected value of a function with x, you can take e in, so you got a times expected value of x plus b. The variance of that, you take the variance in and you square the coefficient of x and you ignore b, because it doesn't affect the variance. If you have two variables, so if z is ax plus by, then the expected value of that would be a times expected value of x plus b times the expected value of y. And that works for any distribution. But the variance will only work for independent variables. So taking the variance in, we have a squared times the variance of x and b squared times the variance of y. Everything is squared. The coefficients are squared. Distribution of a sample mean from a normal distribution. So if x is from a normal distribution with mean mu and variance sigma squared, then x bar is also distributed normally with mean mu but variance sigma squared over n for a sample. And the expected value of x bar is obviously the expected value of x, which is the mean, but the variance of x bar is sigma squared over n. So the standard error would be the square root of the variance. Now it's called a standard error, not the standard deviation, as we're talking about a sample mean, not the population mean. So standard error is the square root of the variance. More means and variances that you need to remember. For a binomial distribution, the mean is np and the variance is npq. For a Poisson, the mean and the variance are both equal to lambda, the parameter. For a function, the mean is x times the integral of x times the function, and the variance, as before, is expected value of e squared minus the expected value of e all squared, but expected value of e squared is the integral of x squared times the function. For an unbiased estimator of the proportion of the population, so calling that p, then it's going to be equal to x over n, the number of successes over the number of tries, which is little p. And the variance is now, the variance of the proportion is pq over n. Compare that to the variance of the binomial. Unbiased estimator for sigma squared, when sigma is unknown, is 1 over n minus 1 times the sum of x minus the sum of x all squared over n. Compare that to the method of finding sigma squared, which was 1 over n times the same bracket. So s squared is our sample variance, which is an estimate for sigma. And if you notice that n times sigma squared is the same as n minus 1 times s squared, because we have the bracket exactly the same. There are other ways of working these out, but this is the one I prefer. You can work them out any other way you want. Right, question 2010. The probability distribution of a discrete random variable x is given by the following table. So x is minus 1, 0 and 1, and theta can be between 0 and a third and is distributed in the table in that way. Obtain an expression for the expected value of x and show that the variance of x is that expression. Let's do that first. So, expected value of x is each x times its probability and the sum of those. So minus 1 times theta plus 0 times 2 theta plus 1 times 1 plus 1 minus 3 theta. So each x times its probability, and that works out to be 1 minus 4 theta. The variance of x comes from using e of x squared minus e of x all squared. So we have to work out e of x squared. And that means I multiply x squared times its probability and add them up. So minus 1 squared times theta, 0 and 1 squared times 1 minus 3 theta, which becomes 1 minus 2 theta. Therefore, the variance of x is going to be 1 minus 2 theta minus 1 minus 4 theta all squared. Multiply those out and we get the expression we needed. So we have 2 theta bracket 3 minus 8 theta. Part B. In order to estimate theta, a random sample of n observations of x is taken. So we're in a sample mode. The mean of the observations in the sample is denoted by x bar. Show that u, which is 1 minus x bar over 4, is an unbiased estimator for theta, and obtain an expression for the variance of u. Now for u to be an unbiased estimator of theta, we need that the expected value of u is going to be theta. So u is 1 minus x bar over 4. I can take the expectation in, so that's the same as 1 minus expected value of x bar over 4. And expected value of x bar is the same as expected value of x, which is 1 minus 4 theta. So gives us theta. Therefore, u is an unbiased estimator of theta. Obtain an expression for the variance. So the variance of u, I take it in and I square the coefficient. I ignore the constant. So I've got variance of x bar over 16. But the variance of x bar is the same as the variance of x over n, because it's a sample mean. Therefore, I've got the variance of x was 2 theta bracket 3 minus 8 theta, and now it's over 16. I can take the n down. So there's the expression for the variance of u. 2 can cancel, so I've got theta 3 minus 8 theta over 8n. Part C. The number of observation in the sample is equal to 0 is noted by n. So show that v, which is n, capital N over 2n, is an unbiased estimator of theta as well, and obtain an expression for the variance of v. Now, if we are talking about the number of observations in the sample equal to 0, we are talking about a binomial distribution. So the probability is 2 theta for x equal to 0. So we've got a binomial distribution, i.e. x is either 0 or it's not 0. So n now is a binomial distribution with n observations and 2 theta as our probability. So expected value of n is np, which is 2n theta, and the variance is npq, which is 2 theta times n times 1 minus 2 theta for q. Therefore, the expected value of v is the expected value of n over capital N over 2n, which becomes 2n theta over 2n, which cancels to give us theta. Therefore, v is an unbiased estimator of theta, which is what we wanted. Explain an expression for v. So the variance of v is the variance of n capital N over 2n, which I can take in squaring the coefficient. So I got variance of n capital N over 4n squared. The variance of n was 2n theta 1 minus 2 theta. I can cancel a 2 and an n, so I have theta 1 minus 2 theta over 2n for the variance of v. Part D, show that the variance of v minus the variance of u is greater than 0, and state then which is the best estimator u of v. Remember, the best estimator has the least variance. So we've worked out the variance of u and the variance of v are those. Taking them away and combining the fractions over 8n. So I've got 4 minus 8n minus 3 plus then 8 theta outside, which cancels to give us 1. 8 theta cancels, so 1 theta over 8n. Theta was between 1 and 1/3, therefore that must be positive. Therefore, the variance of v must be greater than the variance of u, so u is the best estimator. An example from the old WJEC S3 book. The random variable x has probability density function f, given by f of x is theta x plus 3 over 2x squared, where x is between -1 and 1. Theta is an unknown constant. Show that the expected value of x is 2/3 of theta. And then let x bar denote the mean of a random sample. Find a multiple of x bar, that is an unbiased estimate of theta, and express the variance of this estimate in terms of theta and n. Right, so expected value of x is the integral of x multiplied by the function f of x, the probability density function. So f of x, so we've got theta times x squared now, and 3 over 2 x cubed, x times f of x. Integrate that, we get theta x cubed over 3 plus 3 over 2 and x to the 4 over 4, and we need to put in values going from -1 to 1. So we put in 1 first, so we get theta over 3 plus 3 theta over 8 minus, put in -1 in, we've got minus theta over 3 plus, because we're squaring, 3 theta over 8 power 4. Combining those, and we get, so the 3 theta over 8 cancels, so we've got 2 theta over 3, so 2/3 of theta is what we wanted. If x bar is the mean of the random sample, then the expected value of x bar is also the expected value of x, which is 2/3 of theta. If we want some multiple of x bar to be an unbiased estimator of theta, then we need to multiply x bar by 3 over 2. which would then become that the expected value of 3 over 2 x bar is theta. So 3 over 2 x bar is an unbiased estimator of theta. We're getting expected value equal to theta. The variance, now then, so the variance, we take the variance in and we square the coefficient, so we get 9 over 4 times the variance of x bar. And the variance of x bar is the variance of x over n, and the variance of x, we need to find the variance of e of x squared to find the variance of x. So e of x squared would be x squared times the function. So we need to integrate theta times x cubed plus 3 over 2 x to the power 4. Integrate that, we get theta x to the 4 over 4 and 3 over 2 x to the 5 over 5. Putting the values 1 and minus 1 in, we get 1 in, we get theta over 4 plus 3 over 10 and minus 1 in. That becomes plus theta over 4 and minus 3/10, giving us the theta over 4 cancels, so we've got 3/5 coming out for e of x squared. So the variance of x would be the expected value of x squared, which is 3 over 5, minus e of x all squared, which is 2/3 of theta all squared. So that becomes 27, putting them all over 45, minus 20 theta squared over 45. So going back to the variance of 3 over 2 x bar, we've got 9 over 4n times the variance of x, which we've worked out. 9 cancels into 45, 5 times, so 5, so we've got 20n on the bottom, and 27 minus 20 theta squared on the top. So that's the variance of this estimator for theta. Another question. The independent random variables x and y have a common mean, mu, and variances, sigma squared for x and sigma squared for y, respectively. In order to estimate mu, random samples of m values of x and n values of y are taken. The means of these samples are denoted by x bar and y bar, respectively. So show that u, being that expression, is an unbiased estimator for mu for all values of the constant lambda. So we need that expected value of u is equal to mu for all values of lambda. So we can take the expectation into the function. So we've got lambda times expected value of x bar plus 1 minus lambda times the expected value of y bar. But the expected value of x bar is equal to the expected value of x, which is equal to mu. The expected value of y bar is equal to the expected value of y, which is also equal to mu. Multiply those out and we end up with just mu. The expected value of u is equal to mu for all values of lambda, so u is an unbiased estimator of mu. We need an expression for the variance. We can take the variance into the function and square the coefficient. So we've got lambda squared times the variance of x bar plus 1 minus lambda all squared times the variance of y bar. Variance of x bar is equal to the variance of x over m, and the variance of y bar is equal to the variance of y over n. Therefore, sigma squared for x is the variance of x, and sigma squared for y is the variance of y. So we have this expression for the variance of u. We need to determine a value for lambda, which is the best estimator for mu. So we have that as our variance, so we need a least value of lambda, least value of the variance. So we need to differentiate to get a least value, lambda. So we get in that lambda squares goes to 2 lambda times the constant, and then bracket squared goes to 2 times 1 minus lambda times minus 1, the differential of inside. Tidying that up, we get 2 lambda times sigma squared for x over m minus 2 times sigma squared for y over n, and then plus 2 lambda sigma squared y over n. We need that to equal 0 to be a stationary value. Therefore we can divide by 2, so we've got lambda times sigma x squared over m plus lambda sigma y squared over n is equal to sigma y squared over n. Taking that over. Take the lambda out and combine the fraction. So we've got n times sigma x squared plus m times sigma y squared all over m times n is equal to the right hand side. Invert that and multiply, and we can see that one of the n's will cancel. So we've got m times sigma y squared all over n sigma x squared plus m sigma y squared. And that's our least value of the variance. That's a value of lambda for the variance, least value of the variance. Putting that back in to the formula for variance. So we have lambda there and 1 minus lambda there. So we get 1 minus lambda, we can combine that. So 1 gives us n lambda squared plus m lambda squared for x and y respectively. And one of those will cancel, so leaving us with n lambda x squared over the LCM. We can multiply the m squared for the first bracket. We'll cancel with the m on the bottom. So we've got just m times sigma x squared, and n, the n there will cancel, n squared will cancel with the n on the bottom, leaving us with just n sigma y squared. We have a sigma y squared for both, and we have a sigma x squared for both. So taking those out, then we have m times 1 of the sigma y squared plus n times 1 of the sigma x squared left. We can now divide by the bracket, so leaving us with just sigma y squared and sigma x squared over the bottom. Therefore the standard error would be the square root of the variance, giving us sigma y sigma x over the square root of the bracket. For an unbiased estimator of the variance, when you calculate the variance sigma squared of a complete population, you use either that or this. I put it in red because that's the one I like. If you estimate the variance of a population, a parent population, by calculating the variance of a sample from the population using this formula, this estimate of the variance will on average be smaller than the true value of the variance. This is because you are taking square deviations from the mean rather than from the true population mean. The sum of the square deviations from x bar will also always be smaller than the sum of square deviation from either point. So this estimate of the variance is biased. It's likely to be smaller than the true variance. When you use a sample data to estimate the variance of a population, you use a slightly different formula. So S instead of sigma squared for the variance of a sample that we use to estimate the variance of a population, and it's divided by n minus 1, not n. So we use this formula for estimating the variance of the population instead of the 1 divisible by n. And one example, the heights of a group of 6-year-old girls in centimetres are as follows. Calculate unbiased estimates of the population mean and standard deviation of the heights of 6-year-old girls, for all 6-year-old girls. Therefore, adding all the x's, we get 914. Squaring all the x's and adding them, we get 104,732. And we've got n is equal to 8. Now we need those values because when we work out the expected value of x, it's x bar, the same as x bar of our formula, which is the sum of x over n, which becomes 914 divided by 8, which is 114.25 is the mean, is our expected value of the mean of the population mean as well as the mean of the sample. We're going to use this formula now for the variance, an estimate of the variance of the population from our sample. So our sigma x squared was 104,732 minus sigma x was 914 squared divided by 8 and divide the whole answer by 7, so n minus 1. And we get 43.93-ish as our variance. So the standard error, estimate for the standard deviation is s, which is the square root of that, giving us 6.63 to 3 significant figures. Now this is only a small example, as this system is going to be used later on in other examples of FM5. And that's the end of the revision video for unbiased estimators.